Let's begin lecture, and welcome. We have a few announcements concerning the clicking items from exam 2, and I want to go over those with you today. But before we do that, I'll just draw your attention to the quote from Albert Einstein. As I've mentioned before, he was kind of a wise guy, kind of a wiseacre. The hardest thing to understand in the world is the income tax. I don't blame him for saying that. Anyways, about the clicking, there was, as you know, there was a blooper on the test. I forgot to write in on the test form the printout that you were working from, the value of gravity on planet X, 8.33 meters per second squared. I put it on the overhead display for you, but a significant number of you did not do that. So a lot of you used 9.8 meters per second squared. So, and since it was my mistake, I decided, well, all right, I'll give these guys another look. And what I did was I solved out the problem again based on 9.8 meters per second squared instead of 8.33. But I haven't regraded it yet, but I will regrade it. And so, because it's going to give you a different kinetic energy, which was your question number 1, and then a different speed, which was question number 2. And I noticed this Tuesday after the noon lecture, just working with a student. She wanted to look at, Dr. B, I thought I got those problems right. And you know what? She did, but she had them right for 9.8. And so I said, ooh, I better go and see. And there was a lot of people with the correct answers for 9.8. So we'll try to get that squared away. Now, the blooper does not affect the boxcar question. So that won't have to be regraded, but the first two, yes. And also, the code question is not affected by it because the code concept the code question is a concepts question. And so the specific value of G, the specific value of G is nice, but not completely necessary to answer the code question. And in any event, I haven't graded it yet. And also, it has a separate line on your grades page, and that hasn't been filled yet. Now, I put a blurb up for the clicker questions as well as the Scantron questions. I did that this morning, so you might be able to take a look at it. Here's the top of it. I did the boxcar questions first, and then I did the Tweety Tomahawk Jam problem twice, once with 8.33 for planet X, once for 9.8 meters per second squared for planet Earth. And got up early this morning. Sorry I had to yawn there. Anyways, you can look at that on the blurb, exam blurbs page in web courses. It's a PDF, and you can definitely take a look at it. Questions about that regrade before I go on? Yes?
If we have them incorrect, can we go to office hours to get it explained to us?
The question was, if we got it incorrect, can we go to office hours to have it explained for us? You can come to, the answer is yes, and you can come to office hours for any reason. Well, almost any reason. But this is my solution, and it may be sufficient, but definitely if you still want to go over it after looking at this, yeah, office hours. No problema. Another question. Okay, let's keep going. I'm going to do a little recap of the temperature scale concepts, and then we'll bridge into new stuff from this. We talked about Celsius, Kelvin, and Fahrenheit last time. And as you know, the Celsius system, the Celsius temperature scale, it's part of the metric system. It's anchored to the boiling point of water. So I made a diagram here to compare Celsius and Kelvin scales. And boy, these colors do not look very nice. I'm going to have to remember that. This is supposed to be yellow. It looks kind of green. Anyway, so I'm making a vertical one-for-one match between these two scales. So the boiling point is the upper anchor point for Celsius. The freezing point is the lower anchor point for the Celsius system. So that's going to be down here. And then the Kelvin scale is a little bit different. Of course, it has freezing point and boiling point. Freezing point for water is 0 Celsius, as hopefully you know. And the boiling point for Celsius is 100. But in the Kelvin system, you're going to have different numbers. There are officially 100 degrees of Celsius degrees between the boiling point and the freezing point of liquid water. I guess they probably defined it in Paris, France, being as how it's the metric system, which is where the metric system first started, Paris. So that's an important feature because in the Kelvin system, there's also going to be 100 kelvins between boiling and freezing, just different numbers. Kelvin is also considered metric, but its lower endpoint is absolute 0. And this is the place where we have this kind of colloquial notion, Miss Sprauve, that all motion stops. Now, Sir Isaac Newton would have said, yeah, okay, if it gets really cold, average kinetic energy is going to be 0. And you can't have that if a 0 average kinetic energy if all the kinetic energies are not 0. So that kind of colloquially means everything stops. Now that's down here at the bottom. And by experimental measurement, we've kind of determined that spot to be negative 273 on the Celsius scale. Now, the Kelvin proposed that point to be the 0 point of his scale, the absolute scale. And so using that fact and the decision to make each Kelvin the same size as a Celsius degree, so you go up 1 Kelvin, it's like going up 1 Celsius degree, and so on and so forth. That allows you to figure out, the fact that you've got 273 Celsius degrees over here, and then between water and absolute 0 down here on the Kelvin scale, you're going to have 273. But down here, this is the 0 point. And that allows you to do all the conversions that you want to do. And basically, you take whatever the Celsius temperature is and add 273. And if you want to be ultra precise, you add 273.15. And I'm sure that guys can go even more precision than that, but for us, 273 is going to be good. All right, and so, for instance, the freezing point of water is 0 Celsius. Add 273. Here it is, 273 Kelvin. So you can add that to your diagram. The boiling point of water is 100 Celsius. Add 273 to that. Ding! 373 Kelvin. Pretty cinchy. Nothing like going from Fahrenheit to Celsius or. But you know, I did I got up really early this morning, 3 o'clock. And I was kind of laying there trying to get back to sleep, and I was thinking, all right, let me to help myself get back to sleep, let me do something that's really boring. So I decided to convert 98.6 Fahrenheit to Kelvin, and I was able to do that, but I still didn't get back to sleep. So I just got up and made coffee. Anyways, 373, and then down here, of course, is 0. So. And you can think of that one as negative 273 plus 273 equals 0. All right. Now, that's just kind of a recap and a little extra reinforcement. We're going to talk a little bit now about that guy who was on the very first slide, Max Planck. But let me pause for questions about this comparison of scales. Melanie, did you see your grades updated? Yeah, okay. Because Yay! Your sister had a baby? Did you see it? Yay! Nice. All right, no questions. Let's go and talk about this joker. Max Planck. I shouldn't call him a joker. He's kind of a genius. He's a German theoretical physicist. And the letter H, lowercase h, is always associated with Max Planck. I will explain why that is the case and why we have an interest in him. He was a theoretical physicist, grew up in Kiel, in Schleswig-Holstein in Germany, became a university professor in Berlin. He studied thermal physics in the late 1890s, and one of the tough problems that he was working on that nobody else could figure out either until he solved it was the spectrum of electromagnetic radiation that is produced by this theoretical object called a black body. And a black body is this hypothetical object which is both a perfect absorber of radiation and a perfect emitter of radiation. And so being a perfect absorber of radiation, it gets called a black body. And if you've ever seen a cast iron stove, you know, like in your hunting cabin or anywhere else, those are usually painted black for a reason. They're painted black so that they emit all kinds of infrared as efficiently as possible. And that's why he was studying this stuff. Now, nobody could figure it out. You know, nobody could figure out why the spectrum had the shape that it did. You know, there were certain wavelengths that put out a lot of energy and certain wavelengths that didn't put out much, and it all depended on temperature. And nobody could sort it out until he sorted it out. And what he did was introduce the whole idea of the quantum of energy. And his constant, Planck's constant, for which the symbol is H. That's about 1900 he did that. And when he did that, he began the entire modern physics revolution that we call the quantum revolution, or the quantum physics revolution, which has been profound. It's the only way to understand electrons. And without Max Planck, nobody in here who has an iPhone or an Android phone or a calculator would be able to do jack without Mr. Planck and his constant H. Now, I mentioned up here that these theoretical objects, you know, we got all kinds of theoretical idealizations. You know, like the gas that I mentioned the other day. That's an ideal gas. That's the nickname for it. Sir Isaac Newton, he idealized every object as a point mass, having no dimensions, just a geometric point location, even though, the things that he used F equals ma for were not geometric points. So we have all kinds of idealizations, and the black body is an idealization of regular hot objects. And I've done the experiments in the lab. When I was an undergraduate up at NYU, we measured black body spectra. Now, here's what they look like. Depending on the temperature, you have a lot of energy at certain wavelengths. And the hotter the temperature of the object, so this top curve here, this reddish curve, is 5,500 Kelvin. That's pretty HOT. That's way up there. I mean, it would be tough to even look at something that was that hot. But it puts out a lot of energy, that's this scale over here, in these wavelengths up here. And then in longer wavelengths down here at 2,000 nanometers, for instance, nanometers, that's this, the wavelength. NM stands for nanometers. Down here, it's putting out some energy, the red one, but not a whole lot. And then on the other side, short wavelengths, it's putting out energy, but not a whole lot. And in the day of Planck, people could understand a theory of why this part of the spectrum at short wavelengths worked the way it did. And then they could figure out why larger wavelengths behaved like this, but they couldn't figure out how to get them both to bend over and peak and then come back down to the other side. But Max Planck figured that out. Now these are 5 different spectra, and actually this is the visible the visible band of electromagnetic radiation. And you can write it down: visible light, red, orange, yellow, green, blue, indigo, violet, Roy G. Biv, is from 400 nanometers, that's violet, to 700 nanometers, that's red. Okay, and so this is red here at about 700. So the reddest red that you can see is around 700. Now, some of you might be able to see 710. Some of you might only be able to see 695. And supposedly different animals can see deeper into the reds, all the way into the infrared. But 700 for red, and then 400 for violet. And then green's kind of in the middle, so I made this kind of greenish. That green came through nicely. And these particular spectra, a lot of energy in these peak wavelengths. Notice how the peak shifts. For the cooler object down here, 3,500 Kelvin, the peak is way over here at about 1,000. All right? But for 5,500 Kelvin, it's right in the middle of the visible. The peak is right here. That's the greens. And hey, guess what, you guys? These are typical temperatures for many, many stars. Matter of fact, the SUN, the sun, our star, is 5,800 Kelvin. So it's very close to this spectrum. And that is where we get our light. Most of our energy from the sun comes in the visible band. Did you know what color of sunlight? You know how you put sunlight into a prism and you disperse it into its colors? The color that puts out the most energy for the sun is green. Isn't that interesting? And what color are plants on Earth? Green. But why are plants green? They're green because of chlorophyll, but why is anything green? Why do you observe anything that's green that's not a green light? Why? It reflects green light. So here's the interesting thing about plants. And I don't know what the answer to this is. I've never studied chlorophyll. Chlorophyll, right? It makes carbohydrates, sugars. And it's the thing that makes plants green. And it's green to us because it's reflecting the most abundant band of light from the sun. It's like saying, oh, I don't want that, or I'm going to reflect that. I don't know if plants use green or what, but for some reason, that is the way plants work. It's very interesting. Let's take a look at a few other temperatures. Okay, those are stars. And anything has a blackbody spectrum. You have a blackbody spectrum right now. The peak of your blackbody spectrum is in the infrared, which is why night vision goggles are infrared optics. Okay, room temperature, about 290. Human body, about 310 Kelvin. Chemistry class, standard temperature and pressure, STP they call it. 273 Kelvin. In other words, the freezing point of water. So the chemist, the reason they do that is because it's easy to keep things, because ice is so easy to make, they can keep things at the freezing point of water fairly easily. So that's the chemistry lab, standard temperature and pressure. I try to stay out of the chemistry lab. I'd like to go to Mount Everest, but I probably won't go up to the top of Mount Everest anytime soon except in a helicopter. But if you did on a cold night, it would be about 238. I looked it up on the internet. But they don't list it in Kelvin. They just listed it in Celsius, so I converted. Oh, did I say conversion from Celsius to Kelvin? Yeah, let's do a few. Let's do a couple. Because occasionally a textbook will have some. I try to write everything in Kelvin, but occasionally your textbook is going to come up with Celsius. And your exams are going to be all Kelvin, Kelvin, Kelvin. But we may as well know how to get our hands dirty with Celsius to Kelvin. It's pretty easy. Get your clicker ready to click. And we are on frequency B as always. Question number 1. And for those of you that did not get your exam printout on Tuesday, I have them up front here. And if we dismiss a little early today, you'll be able to grab them if you haven't already. 20 seconds. 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Dun, 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 dun. Uh-oh. We got some people that are not listening. 129. Wait a minute. A is negative 129. I believe that's 144 minus 273. So if you guys did this, if you're over here with option A, no, don't do that. It's add 273. Okay. So the correct answer is 417. Most of you did get that. That's good. Yeah.
I thought you said Kelvin to Celsius was add 273.
No, Celsius to Kelvin. Oh, now wait a minute. Let me go back and see that. Wait a minute. You dare to challenge the great Dr. B? Ah! Yeah. Okay. Yeah, so Celsius to Kelvin at 273. All right, you're right. All right, I'll give you guys a free dinero on that one. The correct answer is Highway 417. So if you have a Celsius, always add 273. Yeah, that part of my outline, I had the two words switched. Yeah, that was the error. Yeah. Nope, it's on the podcast. We got to keep going. Here's what you are supposed to do. 144 plus 273. This is accurate. There's an example of the correct conversion process. All right. Now, just a side note for you, exams are going to be like 99% Kelvin all the way, so you won't have to worry about this. But sometimes you'll see a textbook with Celsius in there and even Fahrenheit. You'll definitely see 0% of the test in Fahrenheit. So, now, next question. Raise your hand if you have ever used ammonia for cleaning in your house or anything like that. Bunch of you. All right. Here's a question about ammonia. And hopefully you know the answer to this one. An observable property. "20 seconds. "10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. How come you keep getting up and moving around? He's distracting even me. Yeah, punching older. This one, shh. This one's kind of a public opinion survey, so I have to give you all a point on this one anyway. But that's the correct answer. Now, it's really pungent. All right? And something that's pungent, you only know that it's pungent because it goes into your NOSE, your smell unit, the thing that you perceive smells with. And that means it's a gas. Now here's something that you may, I don't know, hopefully this will make sense to you. The hotter the room, the faster that smell will diffuse around the room. But the colder it is, theoretically, you can freeze ammonia. They have, if it gets really cold, you can freeze ammonia. And then it won't diffuse at all. So the colder, the slower. And my wonderful students, it gets from the ammonia container to your nose because it's in motion. And the temperature, so if I have in a hot room and I open the ammonia bottle 10 feet away from me, it might take 1 minute for me to start smelling ammonia. But if I'm in a really cold room, it might take 20 minutes or something like that before I smell the first whiff of ammonia, NH3. So that means it's in motion, and the motion, the speed of motion is affected by the room temperature. All right? And the room temperature is going to control the temperature of the ammonia gas, because they're going to come to thermal equilibrium. And at that equilibrium, they're going to move around the room at various kinetic energies. Question? What's that?
Does that work with all smells, or is it only with ammonia?
The question was, does that work with all smells or only with ammonia? And every smell that you smell is because of a molecule hitting your, those nerves in your nose. So, and molecules only get there because the only thing that goes in for a normal person, the only thing that goes in their nose is gas, atmosphere, anything in the atmosphere, unless you go swimming and then you get some water in your nose or something like that. But so yeah, it has to be a gas. So molecules, whatever it is. So when you're walking by a bakery and you smell that fresh bread, and you're thinking, oh man, I got to go in and get some fresh, those are molecules attacking your nose. They're floating around in the air. So they're in thermal equilibrium with the air. But a bakery is really hot, and so that means those things go a long way. They go out onto the sidewalk and stuff. So, all right. So just to review, there's zillions of these molecules of ammonia, or the bread smell molecules, whatever those are. Probably some kind of sugar. Some kind of carbohydrate from a bakery smell. Barbecue. You go by. Okay, what's the best barbecue around campus? Four Rivers? Who votes for Four Rivers? I should have made that Who votes against Four Rivers? You don't dare to, see? Okay, so you're walking by Four Rivers, and you smell, oh man, molecules, zillions of them. Random motions, because it's a gas. Now, if a liquid, you can channel. But a gas, I guess you could put a gas in a tube. But a liquid is going to hold together in droplets and stuff, so it's not completely random. And because it's a gas, there's going to be zillions of kinetic energy states, but only one average kinetic energy. All right? So depending on the gas, depending on the temperature, you're going to have an average kinetic energy. And that is why that we say this particular sentence, that the average kinetic energy is proportional to the Kelvin temperature. Now, it's not proportional to Celsius temperature. It's not proportional to Fahrenheit temperature. But it is proportional to the Kelvin scale temperature, whatever that happens to be. And that's why we say, the kind of colloquial concept is that the average kinetic energy is zero at absolute zero of the Kelvin scale for this reason. And my wonderful student, there is a formula for this, but we're not going to really use it too much. But guys have used it to figure out the actual speed of molecules in the air. If you can figure out the mass of a molecule theoretically, you can figure out its average speed. Average speed and kinetic energy is behind a lot of two of the big ideas of heat transport. So let's talk about that, our next big topic for today. And this particular picture of this guy blowing fire out of his mouth from kerosene or whatever. Has anybody in here ever done that? Has anybody ever seen it in real life? Yeah. I would not want to do it, but I guess guys they do it. But this particular picture, so go ahead and write down fire breather. Picture displays all three modes of heat transport. Here's another picture. Now, if you're in the Air Force, you have to be awake in class. Everybody has to be awake in class. And yeah, good. All right. So if you're awake in class, you can get all the notes on conduction. And you won't let me catch you napping. Now, conduction is when you have physical contact between something hot and something that's cold, or something that's warm and something that's cool. So when you touch, like a cold bottle of Pepsi Cola, feels cold to your hand. That means your hand is trying to heat up the bottle. The heat is leaving your hand. It's being transported by conduction. All right? And basically, it flows into the cooler object relatively easy from the hot to the cold. And it raises the temperature of the cooler object. All right? Now, in this particular picture, I like this one because you can see that he's holding on to that little hand torch down to the side. He's got to do that because the kerosene, he spurts it out of his mouth in droplets, I guess, and then he's got to touch them off. It won't work with water because water is not volatile, it's not flammable. Kerosene is barely flammable. It doesn't burn, totally the best, but it'll burn, and you've got to touch it with that small hand torch. Okay, so this guy, it's not fire. It looks like fire's coming out of his mouth, but what's really coming out of his mouth is liquid droplets, and then those get, ignite. You ignite a few of them, and then they ignite the rest of them. You get a chain reaction. Right? Now, counterexample to conduction is insulation. Okay? So some materials like metals are usually pretty good conductors of heat, except some kinds of stainless steel. They're not very good conductors at all. Steel is this interesting alloy that they put different elements in it. It's carbon and iron, and sometimes they put chrome in it to make it stainless. Anyway, stainless steel is not always a good conductor, but most metals are. And the opposite of that is something that doesn't conduct heat. Okay, so if you're on a camp out and you have a campfire going, and you're not asleep in class, but you're taking notes. Oh, he's awake. Okay, good. Good. Don't fall asleep on me, son. Okay. You're in the Air Force. Come on. I don't want you to fall asleep in that B-2 when you're on a mission, right? So you're on a camp out and you put a piece of cast iron, like a rod or something. You put it in the campfire, it'll get red hot, and then the other end of it that's not in the campfire might be so hot you can't really touch it without using gloves or something like that. Versus something made of like stainless steel or some other stuff that doesn't conduct heat very well. Like rock doesn't conduct heat very well. It doesn't absorb heat. It doesn't conduct heat very well. Matter of fact, asbestos is a mineral that for many years was used as an insulator. And that's because it's basically a form of silicon dioxide. I believe it's silicon dioxide. So that's conduction, and the opposite being insulation. Okay, convection. Second mode of heat transport. Now here's this guy. And convection is a bulk motion. If you look at that picture of the fire breather, he's got a fireball, and this is just a photo, a snapshot, but you know that fireball is going upward into the sky. It's convecting upward. And the reason for that is the heat is not conducting away from it into the air very efficiently. Air is a really good insulator. So if you have a down jacket or a fleece jacket, that really just traps air, and it's the air that insulates you. Okay, so if that's not conducting very well, you can get bulk motion. Why? Because if something is hot, it's usually less dense. So this hot air that's all mixed in with that flaming kerosene droplets, that air is going to be pretty hot, and the air around it will not, if conduction is not efficient, then it'll retain the heat, it'll be more buoyant. So the air in the middle of this fireball here, so this is a mixture of air and kerosene the kerosene is ignited, and it's really hot, really bright. And it's heating up the air in the middle of that cloud, but then the air out here to the left and right is still pretty cool, and therefore it rises. Because the warm, like they say, warm air rises. Hot air balloons. They heat up the air in the air balloon, and the balloon takes off. Okay? So that's why this fireball rises upward. Another cool convection example of many zillions that you could talk about is the Yellowstone mantle plume, which in Yellowstone Park, you know that they have geysers and hot springs, and they say that it's a supervolcano that several 100,000 years ago blew its top, or several million years ago, I can't remember which, and threw ash all over the United States, killed a lot of animals, and just buried them in volcanic ash. But that is, Yellowstone National Park is right on top of a big plume of heat, of hot molten lava boiling up from the core of the Earth, all the way through the mantle of Earth, by the process of convection, because the mantle of Earth is, rock in general is not, it's hot, it can get hot, but it's not really a great heat conductor. So that's a good example of convection. Another good example, you can write this down for letter F, 2F, thunderstorms. Every time you see a thunderhead, a thundercloud, that is a huge warm air convection system carrying all that that water vapor. It forms a lot of droplets out of the vapor. They cool and they form droplets, but they're so small they keep going up. And they keep going up until it flattens out. It gets to an altitude where it won't go up anymore. And then that's when it starts to drop those droplets. The droplets get bigger, and you start getting rain all the way down to sometimes hail down at the very bottom of a thundercloud. So a thundercloud, here's another convection system. Florida, more thunderstorms per unit area than just about any place else in the U.S. Also, Hurricane City. A hurricane is a huge convection system for which the source of thermal energy is the ocean itself. And did you know that they can measure when a hurricane goes through a part of the ocean, when it's past there, a couple hours later, the water's a little bit cooler. It's still pretty warm, but it's noticeably, measurably cooler. I think it's like a footprint, a trail of a hurricane through the ocean. It's kind of cool. Third mode of heat transport is radiation. Radiational heat transport. Now this is a little bit different. A way to transport heat away from the sun and to the earth is by electromagnetic radiation, sunlight. So photons of light, they carry kinetic energy and momentum. And then when they hit you, you absorb it, and you're absorbing energy. That is going to heat you up, or heat whatever is absorbing it. And this is true not just for visible light, the Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, part of the spectrum, but infrared, X-rays even, ultraviolet, yeah. Theoretically, radio waves can heat some. Matter of fact, microwave oven is considered radio frequency. And that does heat up stuff in a microwave oven if you have it designed right and stuff like that. So any kind of electromagnetic radiation, if it's absorbed, it's absorbing kinetic energy and momentum, and that will juice up the potential energy average, the kinetic energy average of whatever is absorbing. So if you have a plate of shrimp in your microwave oven, it's going to absorb joules of energy from the microwave radiation. Okay? Your skin cells, they'll absorb ultraviolet. They'll absorb everything, but I mean, when they absorb ultraviolet, you get sunburn. Okay? It's a lot, because ultraviolet there's more energy per photon for ultraviolet than there is for any visible light. And any visible light has more energy per photon than infrared. Infrared's on the low energy side, ultraviolet's on the high energy side. Even astronauts up there on the surface of the moon, they have to be pretty careful because there's no atmosphere. Our atmosphere protects us from a lot of the radiation from the sun. Okay, but you know, if you go to the top of Mount Everest or even to the top of a mountain in Montana and you live up there for a while, you're going to get a lot of ultraviolet. Your clothing will be degraded. You know, especially your synthetic clothing, nylon, any kind of polyester will be degraded by that intense sunlight. So the astronauts on the surface of the moon had to have special shielding. And the reason for that is for every square meter, so this lectern up here that's got the document cam, it's about 1 meter tall. So think of a square about as tall and wide as this lectern where the document cam is. Square meter facing the sun. So if you're on the dark side, if you're on the night side of the earth, you're not facing the sun. But if you're on the day side of the earth and you're facing straight at the sun. So for us, your square meter panel would have to be tilted a little bit. And if you were down at the equator, it'd have to be tilted straight up because the sun comes straight down at the equator. And if you're at the North Pole, it'd be vertical like this, you know, because you're trying to get the sun from the North Pole. It's always in the south. Every square meter absorbs 1,370 joules per second. And that is a ginormous amount of energy when you consider how big the Earth is. And so a lot of, everybody's always worried about global warming and global climate change and stuff like that. There is so much energy pouring into the Earth from the sun every day. It is very hard to keep an inventory of it. And that's why, there's so much controversy about it. It's very hard to do. Figure out all the heat energy and forget about all the stuff that we humans do. But the sun itself, it's enormous. So as a side note, spacecraft, satellites and stuff, a lot of times they have a shielding, kind of a silvery, looks like aluminum foil, but it's called mylar. And it's very thin, very light. If you go to the grocery store and buy one of those little helium balloons, say happy birthday or have a nice day or whatever, those are usually made of mylar because they're sparkly and shiny and they hold helium. And on a spacecraft, they're used to defeat the solar energy gain because otherwise those spacecraft would cook. Another thing that they do on the way to the moon, they just have the spacecraft in a very slow roll. They call it the barbecue roll. And it's going to the moon, and it's just a very slow roll, once every few minutes. It actually rolls as it goes so that there's always a cool side and a hot side to the spacecraft, and it distributes the heat and disperses the heat evenly. Okay, now when you're on the moon, and if you're an astronaut, a lot of times, well, not a lot of times, but all the time, the astronauts, they've got gold coating on the front visor of their spacesuit, and that's so that they can defeat all those photons, 1,370 joules per square meter per second, coming from the sun. Now, this object over here, this is a solar heat collector for your rooftop that you want to be optimized for solar heat gain. So it just depends on your environment and what your task is. If your task is survival, you want to defeat solar heat gain in outer space. On Earth, you want to gain some solar heat. So here's another famous system, SR71 Blackbird. They say that the canopy, the cockpit up here, where the pilot is, that is coated with a very thin layer of gold also to prevent those guys from getting fried by solar radiation, because they fly really high. The U-2 plane really high. So it's kind of, this thing is now retired supposedly. But SR71 Blackbird. Now, there's a cool thing I was able to observe once, and that is, I may have told you this story before. I was looking at meteor showers in August out in Montana, and out there you can see the Milky Way every night, just about, all the stars, and I was looking for meteor showers. The best time for that is after midnight. So I was up about 3 or 4 a.m. before sunup, and I saw this red V-shaped thing come across way up there. It looked like it was right in the stars, but I knew it was and I thought, oh, that's a flock of geese heading south, because it was heading kind of south. I thought, oh, that's a V-shaped, formation of geese, and they're catching the first rays of the sun, and so I could see them from. But then I thought, I was kind of half asleep, so I didn't really think too much about it. And then a little bit later, an hour later or whatever it was, here it comes back going north, and that's when I knew it wasn't a flock of geese, way up there catching the sun. And I thought, oh my God, it's a UFO. So I'm in grad school, right? And so I tell my thesis advisor the next day, yeah, Dr. Hiscock, you should have seen this. I saw this UFO last night twice. I was out looking at the meteor showers. And he's there looking at me like, yeah, what an idiot, But he didn't have an answer, and I didn't either. UFO, unidentified flying object. But what I found out was one of my classmates said, oh, you know what? That's probably the SR71. Because they were practicing that summer. They were training. And so those things, and the reason that it's visible like that is because these things go so fast, the leading edges of the wings get red hot. And even the regular aircraft, you can measure the front edges, they'll get hot from friction with the atmosphere. And that's probably what I saw, or maybe it was a UFO. But what I want to do now is get a handle on how things heat up. So let's do some more work. First thing we need to know is about heat energy. Now, the calorie is the designation that we have traditionally used for a thermal unit of energy. And so it can be converted to joules, and I'll show you that in a second. It's the amount of energy that's required to heat up 1 gram of liquid H2O from 14.5 Celsius to 15.5. So 1 Celsius, 1 gram heated up by 1 Celsius degree, that's a calorie. All right, and that's part of the metric system. So a calorie is a metric system unit of energy, and it's oriented to thermodynamic things, but you can use it for any energy calculation you want. And this device that you're looking at, it looks kind of weird. It's a drawing of a device that was made by a fellow called James Prescott Joule. You have some extra readings, a blurb page now for extra readings about James Prescott Joule and people associated with him. It's linked to the homepage. He decided he thought, that you could convert kinetic energy into thermal energy. So what he did was he took this device. Over here are some weights, and the weight is attached to a string that goes over a pulley, and then the pulley is attached to this axle here, and the axle is pulled by the weight, and so the axle here spins, and that spins these paddles. So when this weight goes negative delta y, it spins up the kinetic energy of these paddles. And then the weight hits the floor and stops. The water keeps going. The water's got all the kinetic energy. The paddles have stopped. So then what you do is you measure the temperature change. So what he said is, I'm going to convert some gravitational GPE into some degrees of temperature, if I can. So you weigh the mass of your water. You weigh the mass and the delta y of your weight over here. You figure out all the joules and stuff. And here's what he figured out. For every gram of water and every Celsius degree, it required 4.184 joules. Okay, this is his discovery. Now, they weren't called joules in his day because that was his day. After his day, they named it joules. But he figured out the thermodynamic equivalent. So for every gram for gram, Kelvin for Kelvin, it takes 4.184 joules of GPE to heat the water up by 1 Kelvin or 1 Celsius degree. Now that's for 1 gram. All right, so that's the size. And people originally did not buy his theory, but William Thomson, Lord Kelvin, was able to get, and you'll read about this when you read about Joule and Kelvin, kind of an interesting pair of guys. Kelvin was able to help Joule get the respectability that he didn't have, but acquired because of the cooperation and collaboration of Kelvin. Now, 1,000 of these calories is equivalent to 1 food calorie. So a food calorie has a capital C. That's how we symbolize that. So a regular thermodynamic calorie is a little c, and I usually write it out CAL, lowercase. Big food calories, capital C, that's 1,000 of the little ones. And that's what you have on your nutrition information on your food, stuff. It's kind of interesting. Anyway, so go ahead and make a note of that, and let's keep going. Here are the basic concepts behind the whole idea of energy flow. So you stir up the water, and that leads to an increase in temperature. Okay, that's nice. And if you have two objects at different temperatures, they're not at thermal equilibrium, so heat is going to flow by conduction or convection or by radiation. Now, if the temperature of substance X here on the left, or this little blob down here, if that's lower than the temperature of Y over here, this other half of the blob, then energy is going to flow to object X because it's lower temperature, and it's going to come out of Y. All right, and so The faster molecules are going to migrate to X more rapidly than to Y. And so you get a lot more of these going from the hot stuff. So I made this curved arrow red. And you get some kinetic energy. You get some fast movers from X, but there's not as many of them. So I made this kind of a pokey arrow in green. All right, so you're getting some high kinetic energy molecules over there. That's true. But there's not as many of them because the average kinetic energy is so low. All right, relatively speaking. Now, you're mixing kinetic energies. You're getting more in one direction than you are in the other direction. And eventually, the two temperatures will be equal. And so you'll still be having kinetic energy swap, from substance X to substance Y, from substance Y to substance X. But if their temperatures are the same, the kinetic energy swapping is at the same rate, so they don't increase in temperature anymore. And that's what we call thermal equilibrium, when the temperatures are equal. Okay, so every time you feel the heat of something outside in the sun, you are not in thermal equilibrium with the radiation coming from the sun. So you got to, get into a building or cover yourself up or something like that. Now I want to give you some more basic concepts now on how to heat stuff up. Now we're going to work on this and maybe have a little bit of homework over the weekend. All right, so let's try to work on this. All right, so if you do have thermal disequilibrium, stuff's going to heat up. Let's get a handle on that. That's our big topic. The quality or the property of a substance that encodes how easy it is to heat up or how difficult to heat up is known as the specific heat. So for water, the specific heat is 1 calorie per gram per Kelvin. That's because 1 calorie of heat energy raises 1 gram of liquid water by 1 Kelvin. All right, so that could be a calorie from sunlight or any other heat transport method, conduction, anything. And so what we say is that the specific heat, C, and it's lowercase c, that's the symbol for specific heat, that's equal to 1.00 calorie per gram Kelvin. All right? And a lot of books, it'll say calorie per gram degree Celsius. But a degree Celsius is the same as a Kelvin. I like to express it in calories per gram Kelvin. So that's what you'll see on my homework and on my test. Now, that's for liquid water. Different substance or the same substance but in a solid state, solid water is called ice. And that has a different specific heat because it's a different thermal state. You've got crystals instead of a liquid. All right, so for solid water, otherwise known as ice, the specific heat is 0.50 calories per gram Kelvin. So solid water is a little bit easier to heat up. You only need half a calorie. For liquid water, you need a whole calorie to get it up, get a gram up by a Kelvin. But for solid water, all you need is half a calorie. Now, what is the difference between liquid phase and solid phase? Liquid water, drinking water, and solid water, ice. Well, the average is that the average kinetic energy is either above 273 or below it. And the other thing that's true is crystalline bonds can form below 273. And those crystalline bonds are actually going to be electrical potential energy because atoms bond electrically. Chemistry is all about electricity, electrons. What are the electrons doing? And so below 273 Kelvin, those bonds can form, and you get ice crystals. You know, six-sided snowflakes, or a cube of ice, or any other form of ice that you may care to think about. And those intermolecular bonds are really important because they store an enormous amount of energy, a whole lot of stored energy in those crystalline bonds. And because that is the case, it's tough to break them apart. So make a side note here. A side note to my yellow side note. The intermolecular bonds are hard to break apart. They represent energy. It takes energy to break them apart. And that is why it takes energy just to make liquid water, it takes energy to make solid water, ice, at 273 Kelvin into liquid water at 273 Kelvin. Now, other substances you look up in a table, right? So, for instance, copper or aluminum or something like that. Now, here's the general formula. For heating up, it depends on how much you've got, what you've got, and how high you change the temperature. All right, so Q equals mc delta T. M is the mass. So that's going to, so for us guys, we're going to be measuring thermal heat Q with grams of mass, usually. All right, we're not going to be using huge kilograms worth of mass. C encodes the substance that you've got. Do you have solid ice? Do you have copper? Do you have gold? Do you have lead? Do you have ammonia gas? You know, what have you got? And then, so for instance, metallic copper, the specific heat is 0.093 calories per gram Kelvin. It's a lot easier to heat up than water, and easier than ice. And then, how big is your heat up? Or, if you're cooling it off, how big is your cool down? All right? Now, I'm going to dismiss you right now. Make sure you write down this formula. I'm going to give you a little bit of homework over the weekend, and then next week we're going to have a big homework assignment Tuesday night. So do your reading. Try to read the rest of Chapter 5, and I'll see you on Tuesday. You're dismissed. Come get your printouts if you need them. Yeah.
I want to show you
Yeah.
this one on here something.
Sweet.
Yeah.
Where was this?
That was on my way back to UCF.
From where?
From Ocala. That was
It's
pretty
fog. It's really low. Really, yeah. Convection, baby.
Yes.
Convection City. Okay, you guys need printouts?
I have 2 answers marked for that question.
I'll take a look at it.
Okay,
I'll
thank you.
give this back to you on Tuesday.
All right, appreciate it.
Okay, you want to get your printout? Okay, let's see. Who needs printouts? Okay, last name?
Right. Mont. Betancourt.
Lidinsky. Mark who?
Okay, B, Bright and
Bright.
Betancourt. Nisha, she left. Okay, Betancourt, Jacqueline. Bright. Oh, let me stop this.